Can you hear me? Yes. Okay, I can hear myself. Mm-hmm.
Okay, we'll start soon. I want to make sure that all the buses are right. We're checking on this. There may be one more. Maybe. Not sure about the bus, but I think we can start. Uh, okay, so let us begin the second day, and we'll have the second lecture by Sandra Fredkin.
So thank you all for coming back. I'm glad you're back. That means I haven't scared you completely yet. So my plan is not to talk about any of my own work in case you haven't figured this out yet. I'm also still not an expert in integrable systems, and I'm unlikely to become one by the end of the week. So any comments, corrections you may have, please share them. The plan for today is to do Jacobians of Riemann surfaces, and I'm not solving any differential equations, and the derivative will never appear on the blackboard today. And I know that at the beginning of yesterday I said motivation was to speak less loudly. Okay. I said the motivation was to try to solve some differential equations, and I have shown you some differential equations. We haven't solved any of them. We will do so next time. So today is going to be mostly about Jacobians. Raise your hand if you have ever had a class in algebraic geometry in your life. Okay, good. Or if you taught a course without having one, raise your hand. Good. Okay, so I wanted to talk about Jacobians. And I wanted to talk about abelian varieties. And I did this last time, but let's try to review this quickly. So an abelian, a complex torus, is abstractly a quotient of c to the g by a lattice, whereby the word lattice, I mean it's a group, an abelian group in c to the g isomorphic to z to the g. So it has two g generators, and it has to be a full rank, which is to say that if I tensor it with R, I get all of c to the g, which is just to say that as vectors in R2G, the 2G generators are linearly independent. That's what a complex torus is. Okay? You can always choose a basis, can always make, G generators of the lattice be a basis, a complex basis of c to the g, and then write the lattice as z to the g, because this is a sublattice generated by the first g generators, plus whatever the other g generators generate, and they generated a copy of z to the g times some tau, right? Where this tau is a g by g complex matrix. Okay? So you can think that every complex torus has a quotient c to the g by such a lattice. Okay, I have specifically chosen this to be the case. If you have a good taste in mathematics, you know that when I say the word complex torus, you should be unhappy. One should define some category, right? And one should talk about morphisms and so on. I'm not going to do that, but we should think about morphisms of complex tori. So what do I mean when I say a morphism? This means in the category I operate in, which means complex. So this means I need to have holomorphic maps of complex tori, right? If I have one object of this form and another object of this form, and I have a holomorphic map from one to the other, I can lift it to the universal covers. I'll get a map of CG to CN. I'm most interested in maps CG to CG. A lift of a map of complex tori will be a map of CG to CG, which has linear growth. And there's going to be a holomorphic map of CG to CG, which has linear growth, which must be a linear map. Okay? So all of this leads me to an exercise, and I should keep my tradition of having some color for exercises. For g equal to 1, which is the classical case of elliptic curves, when two complex tori, which of course you're going to think of as C quotient Z plus Z tau 1 and C Z plus Z tau 2, biholomorphic. Okay, and then you should also ask which complex tori of dimension 1 have automorphisms, endomorphisms. Understanding what these words mean is part of the exercise. I want to say this, and then it's up to you to interpret the problem. Okay? So the correct question would be not which complex tori have automorphisms or endomorphisms, but describe the group of automorphisms or endomorphisms of each complex torus, which would address Pasha's control. I'll continue. Okay? Yes, so this form rings. So that's what it means to be a complex torus. An abelian variety is a complex torus T, which can be embedded in a projective space. This is CPM, right? So an abelian variety is just a complex torus that admits an embedding into a projective space. And there is a theorem, which is Riemann's bilinear relations, which says that a quotient, as described above, in this form, is an abelian variety if and only if tau is symmetric and the imaginary part of tau is positive definite. Nice exercise, but maybe exceeds the real scope of an exercise. Okay. So I'd be interested in abelian varieties, and let me now tell you why I'm interested in this. Well, you'll see this shortly. So if I have X is any algebraic complex variety, polarization on X is the C1 of an L, where L is an ample line bundle. On X. I don't want to define what this is. This is not where we're going. But I want to say that if X is smooth, a polarization is just a class, C1 of L, which is a Schurn class of a complex line bundle. So it's going to sit in H11 of X with complex coefficients, which is positive. That's what I write, positive. It makes sense to talk about positive classes. They give me a pairing, and I want it to be positive. But it's also a C1, so it better be an integral class. Okay? So that's what it means to have a polarization. A polarization is a class of a positive, ample, however you want to think about it, line bundle. That's what it is. I don't want to say what ample is. You can ask what this means for an abelian variety, and this is easy to see. The homology of an abelian variety, the homology of a complex torus is very easy to compute, right? It's just generated by H1. Okay? A polarization is called principal. L, C1 of L is called principal if the dimension of the space of sections is precisely 1. Okay? Does this clarify a little bit what we did last time? Or I repeat it. Am I too loud, or am I the only one here in an echo? Okay, I'm good. Okay, so I now want to tell you an ad hoc, I guess the physicist would like to say the word ansatz. I'm not going to say the word ansatz, for why this is true. So I want to tell you, given any tau, which is like this, right? So it's a G by G complex matrix, which is symmetric with positive definite imaginary part. I want to tell you how to define a principal polarization of this quotient. So definition. For any tau in the Siegel space, so this is a Siegel space. This is what I wrote last time also. So this are G by G complex matrices satisfying the condition that they are symmetric and positive definite. And for any Z, which is an element of C to the G, the theta function, theta of tau and Z, whether you call this tau or tau depends on which side of the Atlantic you're going to be. I'll keep saying tau probably. And this is either Z or Z, depending on which version of English you speak. So this is theta of tau and Z. I'm American. Okay. This is the sum over all integers n and of the exponential of pi I n transpose tau n plus 2z. Okay. Something. I wrote a formula. We should convince ourselves that at least we know how to read such a formula. This is a g-dimensional vector. This is a g-dimensional vector. I can take scalar product. This is a g-dimensional vector. This is a matrix. This is a vector. So at least what I wrote makes sense. The fact that the tau is symmetric makes this nice. The fact that the imaginary part is positive definite makes this convergent. Because morally things, this is like I, right? The imaginary part is positive definite. So this is like exponential of minus n squared. This is what makes it convergent. Of course, the actual proof is a bit more complicated, but morally, that's what the proof is. So, exercise. This is an easy one, but this is just to familiarize yourself with the formula. It says the following, that for any m1, m2 integers, theta of tau z plus m1 plus m2 tau is equal to theta of tau z times some non-zero factor depending on m1 and then m2. Which part of the exercise is to write this factor explicitly. Okay? This is reasonably easy to check. You basically just need to rearrange the summation so that it goes differently. Okay? I'm not going to go into this. This is an easy exercise. Why am I telling you that? Because this means that this exercise has a corollary of. Pasha, don't spoil the exercise, please. The dependence is allowed to be trivial. I never said anything else. Yeah, so of course Pasha is correct. So the theta function is just periodic with respect to M1. So this does not depend on M1. Also, I have hopefully by now, yes, I have made the traditional mistake in the field. So this is tau times an integer. Here I wrote integer times tau. I should be doing the same thing always, and I was very carefully sloppy. So whether you multiply on the left or right should be done consistently. I have not bothered. When you're doing the exercise, you'll figure out the right way to multiply. Okay? Otherwise, it won't work. So the corollary of the exercise is the following. I can define a locus theta tau inside a sub tau. So this is the quotient, right? C to the g, z to the g plus tau z to the g. Hopefully by now, no, I haven't yet messed up. So this is a locus defined by the following. Theta tau is the locus of z in a tau such that theta function vanishes, is well defined. What do I mean by this? Of course, I've written a function. If you trust me, this is a well-defined holomorphic function on C to the G. Of course, its zero locus on C to the G is well-defined. But I claim that its zero locus descends to the abelian variety, right? Which is to say that the zero locus is independent under translations by this lattice, right? But that's exactly what this exercise says, right? It says that if I add an element in this lattice to Z, whether this is zero is the same as whether this is zero, right? The zero locus is independent. It doesn't mean that the function is the same. It just means that I've multiplied by a constant. Constant means this non-zero factor does not depend on Z in particular. Okay? So this is called the theta divisor. Fact. Fact means I don't want to prove it. I don't want you to prove it, but I want you to believe it because we have to. Theta tau defines a principal polarization on A sub tau. Okay? Let's parse what this says. So the theta tau is a subset of A sub tau. It's a codimension one subset of A sub tau. So it's a divisor on A sub tau, right? It has a homology class, which is a class in H11 because it's a complex subvariety of codimension 1. It's a well-defined subvariety, so it's an integral class. I'm claiming that it's an ample class, which I'm not proving. I'm moreover claiming that the dimensional space of sections is 1. This is a bit sloppy, so from now on, when I say polarization, I will pretend that I can think simultaneously of three things: an ample line bundle, its Chern class, and the section. Okay? And I will write theta for all of the above just to confuse you. Okay? Beware that this is sloppy because I can take the theta and I can translate it. Remark, for any point V, let's say, in the abelian variety A sub tau, I can translate theta by V, which is to say, consider the zero locus of Z such that theta tau Z plus V is 0. Okay? If you're thinking of this as a subvariety of C to the G, this means you just translated it by, well, either V or minus V, depending on how you think about things, okay? This will be my convention. I want to write it on the blackboard. And the Chern class of this is not going to change, right? So this, for me, will be denoted translation by V of the theta divisor. Its Chern class is the same class, but of course it's a different function. Yes, Pasha?
Yeah, maybe it makes sense to mention that this theta tau is not analytical line 1 will defined by set.
I could say all of this, but I won't. I want to go in another direction. Yes, there is quite a bit of stuff hidden here, of course, right? Um, you need to check something. There are some choices involved. I wrote some formula, right, which is really a formula dependent on a point in the Siegel space. The isomorphism classes of abelian varieties are not the Siegel space, but a quotient by the complexity group, which I'm not going to write again. And I'm also claiming this choice is reasonably well defined under the action of the complexity group. There are many things that I'm hiding, but this is not the direction I want to go to. Okay, any questions so far? So, I mean, I wrote an explicit formula for an explicit function, and I made some claims about that function. Are the claims okay? Yes? Okay. This is what I wanted to say about abelian varieties. Mostly, one last thing is, of course, that AG is the moduli stack. Yeah, maybe I should write this quotient. Moduli stack, moduli space of principally polarized abelian varieties. And as I said last time, it's a quotient of the Siegel space by the complexity group, by the integral complexity group. And I don't want to discuss this as an exercise today in the exercise sessions, but I'm happy to discuss this privately. So this is basically clear from the description we have done so far. And in particular, what you can observe from here is that the dimension of the moduli space of abelian varieties, I claim that it's a complex stack, manifold. So it has a well-defined notion of dimension, which is the same as the dimension of this gadget, right? Because I'm taking a quotient by something discrete. The dimension does not change. What's the dimension of this gadget? This is symmetric G by G matrices. Okay, we know the dimension of that. With positive definite imaginary part. Well, that's not open condition, so it doesn't change the dimension. So the dimension is G times G plus 1 over 2, by which I mean, of course, the complex dimension. And that's the dimension of the space of complex G by G matrices, which are symmetric. Okay? Now, the next plan is to go to Jacobians. Okay? All good? Questions, complaints, corrections? Yes? Because I'm more used to writing it this way, but I have already made many mistakes about left or right. So if I write this on the left here, this should mean I should write tau on the left or right correctly. The Siegel upper half space is really a locally symmetric space. It's a quotient of SP2G. I mean, I will admit, but not in public, the Siegel upper half space is really SP2GR quotient by UGC. And if I write this quotient on the right, I better write the other quotient on the left. I have to make, once and for all, I have to make consistent choices. But there is only one choice to make. So if I write it this way, then whether the lattice is tau times z to the g or zg times tau, I should also know which one is correct, except I'm not bothering with this. Okay? If you look at the papers in the literature, half of the papers make this mistake somewhere. So it's fine. Okay? So Jacobians of curves. So I wanted to tell you or remind you about what divisors are. So my curve continues to be denoted C, with apologies to Pasha, who I think denotes curves by X. But I'll have to stick to that. Okay. But that's not the same curve C. So I'll have curve C. And I want to say that, I want to remind you, so that a divisor on C is just a sum of mi pi, where mi are integers and pi is a point on C. It's just a formal linear combination, finite sum. Okay? The divisors on C form a group. There is a degree map from divisors to integers. Which just takes the sum of all the coefficients. Okay? If I have a function f on C, so it's a function which means a meromorphic function, so it's a map from C to P1, then the divisor of f is the following. It's a sum of zeros of f, zeros z of f, times the multiplicity of f at the 0 minus the sum of multiplicities of the poles. Okay? Which I can also write as just the sum of all points P and C of the order of f at P times P. Okay? So the divisor of a function is the sum of its zeros with multiplicity minus the sum of the poles with multiplicities. This is manifestly a finite sum, right? Because there are finitely many zeros, finitely many poles. I write it schematically this way. You should complain. This is a sum of all points of C. This is certainly not a finite sum, right? But the coefficient is the order of f. The order of f is 0. It's a regular point for a generic point of P. So this is the same, it's just a shorthand for this, if you wish. Okay? That's what a divisor is. Then Picard group of C is the group, divisors are denoted divisors, quotient by divisors of functions, called principal divisors. So the divisors on C are an abelian group, right? I can add two such expressions just formally together. And then there is a subgroup of this group, which is obtained by taking divisors of functions. So I better convince you that this is a subgroup. Well, this is easy because I can just tell you the divisor of f times g is equal to the divisor of f plus the divisor of g. Okay? So this is a subgroup, and the Picard group is the quotient. This admits a map called the degree to Z. I told you what this map is here. I claim that the divisor of a function always has degree 0, otherwise this map would not exist, which you know under the guise of the statement that the number of zeros of a function is the same as the number of poles of a function counted with multiplicity. So the degree is 0. Okay? I said it's. Okay. I'm happy to have a constant map, by the way. That's not a problem. The divisor just is not there. Okay? If I'm writing this way, I should also write that f is not identical equal to infinity. But yeah. There were so many things I was hoping to happily skip and sweep under the rug. No, I'm not allowed. So Pasha, I'll tell you when you're supposed to not notice. Okay. How many of you have seen the definition of the divisor group and the Picard group? Okay, good. So you can define peak D inside peak. These are the divisors or degree D divisors. And there is, of course, a fact that Picard, D of C, is the line bundles on C of degree D up to linear equivalence. Okay, which Pasha, of course, alluded to yesterday, and I'm not going to prove. Okay, so definition. This is a not very nice definition. I want to tell you what the Jacobian of C is. I told you last time, I took integrals of a basis of homology and so on, but I can just tell you that this is peak, say, G minus 1 of C. Okay? This is just a definition. Notice that this is isomorphic to peak D of C for any D, but this is not canonically. It's just this isomorphism is given by some D in peak G minus 1 minus D. So if I take an element D in peak G minus 1 minus D, I can just add it to any divisor here, and I'll get an element here, right? So if I take any line bundle, any divisor, I'm being sloppy with language because I want to be sloppy with language, of this degree, and if I add it to any divisor of this degree, I'll get a divisor of degree, the sum of degrees, so it's here, right? But this isomorphism depends on this choice of D, okay? I want to think of it this way, because if I think of it this way, I can tell you what the polarization is. This will be principal polarization. On peak G minus 1 of C. So theta is defined to be the locus of effective divisors. Effective means linear combinations with only positive coefficients. So I'll write this as not a sum, I'll write this as P1 plus dot 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 plus Pg minus 1 inside peak G minus 1 of C. So let me try to explain something. So what I wrote here is a linear combination of arbitrary G minus 1 points in the curve, right? This is manifestly a divisor of degree G minus 1. Of course, in peak, I'm not thinking about this. I'm thinking of its equivalence class up to principal divisors. But what I wrote is something, well, there is something to check, but what I wrote, this looks like it should be of dimension G minus 1 unless they're somehow linearly equivalent to each other easily. I never told you, of course, but the dimension of the Jacobian of any peak is equal to G, right? So I have defined for you a locus of dimension G minus 1 inside the locus of dimension G. So it's a divisor, it's a codimension 1 complex subvariety. The claim is that this is an effective divisor. Well, that's clear, I defined the locus, so it's an actual subvariety. The claim is that it's ample and has one section. This I'm not going to prove, but that's the definition of the Jacobian. This is not a definition of a Jacobian that is truly the best, because if I define it this way, it's not clear that Jacobian is a group. And that's not nice. So I'll make one apologetic remark about that, and then I'll forget it. Remark: there exists a natural map, natural, canonical, I don't know what to say, peak node of C times peak node of C to peak node of C, which is just the sum of two divisors, right? So I take a divisor D1 here, and I take a divisor D2 here, and I send it to the sum of two divisors, right? There does not exist a natural map, natural, canonical, whatever, peak G minus 1 of C times peak G minus 1 of C to peak G minus 1 of C, right? Because if I have a divisor of degree G minus 1 and another one of degree G minus 1 and I take their sum, I'm going to get a divisor of degree 2G minus 2, which of course I can then identify with divisors of degree G minus 1, but there is a choice involved. However, I can do the following. So if I take a divisor D1 here, and I take a divisor D2 here, I can consider D1 plus D2. That's a divisor of degree 2G minus 2. And I can subtract from this the canonical divisor of the curve. the canonical divisor is the divisor of any holomorphic differential in the curve. So this has degree 2g minus 2. So this gadget lies in peak node of C. Okay. Moreover, peak g minus 1 has a natural involution. Just take d to the canonical minus d. This is responsible for the serial-duality, essentially. Okay? I'm not saying anything further. But this is just to warn you that I would like to think of the Jacobian as peak g minus 1, because then I can see the theta divisor, the polarization inside it very naturally. But I'm losing the natural group structure, so there is some choice involved. The choice is really not so big because somehow I need to identify peak node and peak g minus 1. If I wanted to identify peak node and peak 2g minus 2, I would have a canonical identification, which is what I used here, the canonical class. So I should really use a square root of the canonical class, which is known in classical literature as Riemann's constant. But I'm not going to go that way. I'm going to pretend that this issue does not exist.
The second method we find is from G minus
To peak node, okay? Because this was a degree g minus 1, another degree g minus 1, total 2g minus 2. So I always have a map from peak A times peak B to peak A plus B. But then I have the class, canonical class, which has degree 2g minus 2. So it ends up in peak node. Okay? Okay. Any questions so far? Yes. How do I see that the theta divisor is dimension g minus 1? Because each of the points pi here, right, is a point on the curve. The curve has dimension 1. So I've written a g minus 1 dimensional set of sums. Of course, I'm then taking a quotient. So you might. But I don't know how to sum points. I mean, this is a sum. This is divisor, right? So I don't know. I mean, I don't know how to add points on the curve except to think of the sum as a formal sum, which is a divisor, right? A divisor is a linear combination of points with some weights. So I've chosen all my weights to be 1. And I've chosen to have g minus 1 points. This does not prove that the theta divisor has dimension g minus 1. Because I'm mapping, I mean, as a set of divisors, yes. But then I'm taking the equivalence by principal divisors, by divisors of functions. So this could in principle cut down the dimension. I'm claiming this doesn't happen, but this requires some thought. More questions? Okay, raise your hand if you were aware of all this so far, somehow, more or less. Okay. So this number will now go down a bit, probably. Theorem, Riemann theta singularity theorem. So before I say this, let's recoup where we are. So in the beginning, I spent some time talking about modular of abelian varieties, right? And I somehow pursued it analytically. I wrote tau, I wrote the theta function, I wrote the theta divisor inside the given abelian variety. There was a formula. You have an exercise to prove that this actually makes sense, right? Then I had a more algebraic today, the more analytic was yesterday, construction of Jacobians of Riemann surfaces. This is a theorem that describes geometrically better than that what the theta divisor of a Riemann surface looks like. There is no analog of this for a general abelian variety. There are many, many questions about theta divisors of general or somewhat general abelian varieties that are not approachable because there is no analog of this statement. So this is very, very special to Jacobians. The statement I'll write very quickly, and then we'll spend some time parsing it. It says the following. It says for any, I'll write L because I'm thinking of this as a line bundle. So for any degree g minus 1 line bundle on the curve C, which remember is a Jacobian, if I take the multiplicity of the theta function, or the theta divisor, at the point L, right? So the theta divisor is a divisor in here. It's also given by a function. It makes perfect sense to compute its multiplicity, except I should write. It makes perfect sense to compute the multiplicity of a divisor theta in the Jacobian at a point corresponding to L. This is a bit confusing because this is a line bundle on a curve, but this line bundle is a point in the Jacobian. At this point of Jacobian, I can take the multiplicity of this. And the answer is that this is just the dimension of the space of sections. Okay? This is a grand generalization of that statement, right? Because what does it mean that the multiplicity is greater than 0? It means I have a section. If I have a section, it means I can write the line bundle as that. What is a section of a line bundle? A section of a line bundle is, of course, a section of a line bundle. But I can also think of sections of line bundles as meromorphic functions, which I'll remind you of in a second. This is much, much stronger than that. And this sort of describes, quote unquote, completely the theta divisor of a Jacobian. Quote unquote completely, because it only captures the multiplicity. There are many more invariants you may want to know. This is much more elaborate. Okay? So what I'm referring to when I was saying something about functions is recall that if L is a line bundle on C, which corresponds to a divisor D in some group of divisors of degree C, then H naught of L is a set of meromorphic functions on C, meromorphic functions F on C, such that the divisor of F plus D is positive, non-negative, which is to say that the multiplicity of every point is non-zero. Hopefully I didn't mess up any signs. Okay? So I'm just saying that how do you think of line bundles? Well, you think that's a line bundle, transition functions, that's all very good. This is all correct, of course. For curves, for Riemann surfaces, a divisor is the same as a point, right? It's a codimensional one thing on a one-dimensional complex curve, so it's a point. So a point is the same as a divisor, the same as a line bundle, right? And then I'm just thinking of, I can trivialize a line bundle outside of a finite collection of points, as Pasha described yesterday. And that's how you can perceive then the sections, okay? I don't want to go too far this direction because that's not the direction we're going. If you have never seen the Riemann-Roch theorem, I have never thought about its proof in this classical spirit, I do highly encourage you to think about it. This is not an exercise that you can really do, but please do think about it if you get a chance. Okay, let's see. Any questions? Exercise. First, for g equal to 1, okay, you have a curve C. Please establish that it's canonically isomorphic to its Jacobian C. What does Riemann theta singularity say in this case? For g equal to, how is C related to the Jacobian? And what does the Riemann theta singularity theorem say then? There is a nice uniform answer to this question in genus 1 and genus 2. All curves of genus 2 sort of look the same. All curves of genus 1 look the same from this point of view.
So the way you define Jacobian, so for G equal 1, it has a 0. Because you said it's big G minus 1. But the curve of genus 1 doesn't have a 0. So this is not canonical.
Did I write canonical?
You said.
Oh. Is it true that M1 modulo of curves of genus 1 is equal to A1? Okay? I don't want to comment on that, and Pasha will not comment on this now. So this is this question admits both answers, yes and no, depending on how you think about it. Both are correct. Okay? Okay? This is not something we're going to discuss, but if you really want to check that you really can follow the machinery, figure out what happens for genus 3. So you will discover here from this point of view that not all genus 3 curves are created equal, and you should be able to see how they're not created equal. Tell me what this means. And what can you say about the singularities, right? Is the theta divisor of a Jacobian of a genus 3 curve singular? If it is, what are its singular points? What do the singular points look like? Okay. I mean, I'm aware that look like is not a mathematical term, but this is what I would like for you to think about. Okay. Any questions? Okay, so I want to proceed more in this direction, but let's do an interlude. Yes. A divisor, a Cartier divisor, or any divisor on a smooth manifold, you didn't hear that, is given by a function. And you just see with what multiplicity this function vanishes the point. So if the function will vanish, its first order derivatives will vanish, its second order derivatives will vanish. That's all. Huh? Wait. I'm very glad that I can. So let's parse this statement again. What is L? L is a line bundle on a curve. As such, it's a point. So this guy here is a point on the Jacobian, right? Yes, I'm aware that it's represented by a line bundle, but the Jacobian of a curve is the moduli space of line bundles on this curve. So as such, L, which is secretly a line bundle on the curve, represents a point on the Jacobian. The Jacobian is peak G minus 1. Theta is a divisor on the Jacobian, right? Or you can think it's the zero locus of a theta function on the Jacobian. So this is a divisor. Theta is a divisor here. So I can ask what is the multiplicity of a divisor on the Jacobian at a point on the Jacobian. And it turns out to be equal to the dimension of the space of sections of the actual line bundle L on the curve. So it relates two very different things. It relates the geometry of the Jacobian here to the geometry of the curve here. Okay? Make sense? And this is indeed extremely confusing because I'm taking multiplicity of a divisor on the Jacobian at the point of a Jacobian that corresponds to a divisor on the curve. And that's what this says, right? And there is no way around it. This is what this statement is. Okay? Let me do an interlude on the Schottky problem, and then we'll return here. Maybe by that time some more questions will arise. Interlude. It's not really interlude. It just doesn't follow in the logically from what I was saying. Schottky problem, which I have alluded to in the beginning. So moduli of curves is denoted mg. Moduli of abelian varieties is denoted ag. There is a map that sends a curve to its Jacobian, right? Theorem, this is called J, for Jacobians. This is Tarelli's theorem, which is to say J is injective. And I'll write here something you cannot read. So this says on coarse spaces, but I meant it to be invisible, and I succeeded. So this is an injective map. So what does it say in words? It says that if I tell you an abelian variety and I promise to you it's a Jacobian, you know it's a Jacobian of what curve, right? This can be quickly proven from here if you follow the machinery. We're not doing this. There are many, many proofs of the Tarelli theorem. That's one of the cornerstones of the moduli theory, many classification problems. This is the first instance of Tarelli theorems from Hodge theory because the Jacobian is a classifying space for weight 1 Hodge structures. And this captures the geometry of the curve. But this goes far beyond what we're discussing. What's the dimension of the moduli space of curves? The dimension of mg is 3g minus 3. This is a very nice thing to check, except you won't be able to prove it unless you know that it's really a manifold or an orbifold. But this is, the computation is essentially due to Riemann, modular many things that need to be fixed afterwards. The dimension of this space is that, right? You can check what they are, and they're both irreducible. And in fact, the Jacobian map from M2 to A2 or from M3 to A3, they are dominant maps. Dominant doesn't mean they're isomorphisms. It means the image is dense, right? So this means basically every abelian variety of dimension 2 except some smaller, some codimension subset is a Jacobian of a curve. Any genus 3, any three-dimensional abelian variety, principally polarized abelian variety is a Jacobian of a curve up to smaller dimension subsets. You can check 3 times 4 over 2 is 6, which is the same as 3 times 3 minus 3, right? So you know that this is going to fail. So theorem, this is due to Schottky and goes back to happily 1880s. The proof, of course, was incomplete. So the proof was completed by Agusa in 1970. It says the following. I can write for you the solution of the Schottky problem. I'll write what the statement is, and I'll say this is a solution of the Schottky problem. The question is to know which 4-dimensional abelian varieties are Jacobians of curves. It's
Maybe for the first identity, you need minus 3, you should say that G.
well, this is why I started with M2 here. But since we don't really know whether M1 is A1, that was an exercise, right? So the statement is the following. So I want to know for a given abelian variety, which I'll write as A sub tau, right? Remember A sub tau, which is a 4-dimensional abelian variety, okay, is a Jacobian of some curve, so lies, so this is to say A sub tau lies in the image of M4, if and only if the following condition holds. So the sum theta epsilon delta to the 16th power of tau, 16, 2 to the 4th, is equal to the sum theta to the 8th power epsilon delta tau. Let me put a 0 here. Squared. I'm not done. I have to explain to you what I wrote. Where theta epsilon delta tau 0 for epsilon and delta in z mod 2z to the fourth is essentially, I mean, there is some constant, which I don't want to tell you, depending on epsilon delta, but it's just the value of the theta function at the corresponding two torsion point. Okay? So these are the so-called theta constants. And basically what they are, they're just the values of the theta function at various two torsion points. So two torsion means if I multiply by 2, I get the lattice vector. So it's a point on the abelian variety a sub tau, such that 2 times that point is the origin. Okay? There is some constant factor which is easy to write. I just don't want to bother because we'll never write theta constants again. And so I don't want to waste time in that direction. Notice that this is an amazing result, I think, because this is something that relates two kinds of geometry. So this solves the Schottky problem. This describes the image of the moduli of curves of genus 4 within the moduli space of abelian varieties of dimension 4, very, very explicitly. If you have a computer, you can check this in no time whatsoever, right? This is a very nice algebraic equation. It fits here, right? I could write it on the blackboard in half a line. I can remember it. I don't have to look at my notes to find out what it is. It's completely explicit. It's one equation because you would expect that this is one equation, because if you think about the dimension of A4 is 10, the dimension of M4 is 9, so it's codimension 1, so it has to be given by one equation. It's a divisor. Okay, that is the equation. Okay, and I have written it explicitly purely in terms of the theta function. Okay, this is a solution of the Schottky problem. So the Schottky problem is the following problem, which is really the goal of this lecture is to present you a solution to the Schottky problem due to Igor Krichev error by flexes of the Kumho variety. We'll get to there. Is to describe the locus of Jacobians of curves within the moduli space of abelian varieties. And this solves the Schottky problem completely for g equal to 4. Okay? Yes? There is. I wrote a theta function explicitly for abelian varieties. The formula I wrote was for abelian varieties. Theta of tau z is a sum of exponentials. That was for any tau in the Siegel upper half space. That knew nothing about the curve. The Riemann theta singularity theorem is something very interesting about curves and so on and so forth. But my formula for the theta function was theta of tau z is some sum of exponentials. That just uses tau, which is a matrix in the Siegel upper half space, a symmetric matrix with positive definite imaginary part. And that's all I need to define this function. I never said that. There is a theta function for abelian varieties. There is no theta singularity theorem of any kind. I have no idea how to do that. But the theta function is well defined. The theta function is the polarization, right? So the principally polarized abelian variety has a principal polarization, commonly denoted by theta, written explicitly analytically in the formula I wrote down. That's there. For a Jacobian of a curve, the theta function has this beautiful geometric structure, which is lacking for a general abelian variety. But this is well defined for any point in the Siegel space, really. That's what I wrote, right? Of course, this is a Siegel modular form, which are words I'm not going to say. So this is well defined not on the Siegel upper half space, but on the modular of abelian varieties, but never mind. More questions? Yes. On a Jacobian of a curve, yes. Correct. So I defined theta function in two different ways. I defined the theta function by a formula sum of exponentials for any principal, for any abelian variety. For any tau in the Ziegler-Lapa half space, which is the universal cover of the modular space for abelian varieties, I defined the theta function. I defined for you a theta function completely differently here for Jacobians. And the claim, which I never wrote on the blackboard, is it's actually the same thing, which by no means is clear, right? You need to say something. This is somehow miraculous. That this is the whole point of this is that I'm relating two different worlds. This is very arithmetic, right? Abelian varieties are sort of, there are modular forms, there is some arithmetic, there is very little geometry. It's very hard to introduce some interesting geometry on abelian varieties. They're too flat. The curves are much more geometric. There is lots of interesting geometry on curves. And this story relates the two successfully. And this is a geometric description of the theta function for Jacobians. The theta function, if you view this as this exponential sum, it has a very different nature, but this tells you some geometric properties. Thank you. Any more questions? I have defined a principal polarization for every matrix tau on the Ziegler-Lapa half space. I could have equally defined a non-principal polarization for every matrix tau in the Ziegler-Lapa half space. So if there is a thing called modular space of non-principally polarized abelian varieties for a given type of polarization. If I think about its universal cover, it's also the Ziegler-Lapa half space, but that be taken a quotient not by sp2gz, but by another arithmetic subgroup. So I have made some choice, which I concealed. But what I have defined defines for any point in the Ziegler-Lapa half space, there is a canonical way to associate to this tau in the Ziegler-Lapa half space a principal polarization. Non-principally polarized abelian varieties will never be touched in these talks. They will never appear, which is why half of the time I probably just say abelian varieties and I mean principally polarized. More questions? Okay, let me continue for another blackboard with the interlude on the Schottky problem. Okay. So, as I said, this is a complete solution of the Schottky problem in genus 4. I know precisely what the image of the moduli of curves of genus 4 is within the modular space of abelian varieties. There is no such explicit solution, some such explicit characterization of the Jacobian locus within the modular space of abelian varieties for any G at least 5. Okay, this is. I mean, we haven't made progress, you might argue, in 150 years now, 140 years, right? That's not quite true. But nothing like that is known. In genus 5, we don't know. Some things are known. Where I'm going is a solution of the Schottky problem. It's a complete solution. It's less explicit in some ways, more geometric in some other ways. If you look at this equation, it's very beautiful, I think, combinatorially, whatever combinatorics means here. But if you ask me what the geometric meaning is, I'd be stuck, right? I mean, I do know, but not in a direct way. This is some formula. So some things are known. So maybe I should justify why I have been invited here. So I'll state a couple of results, which I'm not going to talk about, but where I have been involved. Theorem. This is joint work with Riccardo Salvatimani. It says the following. If I take this wonderful equation here, and I just write it in genus 5, it is not satisfied. on the Jacobian locus of curves of genus 5. That is a thing that's very easy to generalize. What I've written here was, some sum. I can write the same sum in genus 5. I should replace 2 to the 4 by 2 to the 5 for some obvious reason. And then there was a conjecture of either Belavin and Knizhnik or Docker and Fong, which was to say that the cosmological constant for E8 cross E8 and O16 superstring theories are the same. And no. Okay? So this doesn't work. So you cannot just generalize this equation and write something like that. However, there is something you can do, and this is joint work with Herschel Farkas and Riccardo Salvati-Mani. And this is all recent. I mean, I was not alive when Schottky did his work, so this is much more recent than that. There is an explicit set of equations in theta constants we shall call F1, Fn, where n is the codimension of the Jacobian locus. Such that the Jacobian locus, its closure really, is an irreducible component of the locus where all of these are 0 inside the modular abelian varieties for any genus. Okay? This is a so-called weak solution to the Schottky problem. Weak means that you don't characterize a locus, you characterize the Jacobian locus up to extra components. There is a long story of this. The first weak solution was known to Andreotti and Maya. This is a so-called Andreotti-Maya locus. There is a whole theory of that. We're not going that way. These equations are explicit, but they're not explicit enough that I'll just write them down on the blackboard from memory. And if I were, they would take up the entire blackboard. There are some nice combinatorics. We're very happy with them. You can check them. It's not so bad, but that's about it, right? They're definitely not enough to characterize a locus. They don't give a solution. So there are definitely other components. Absolutely, yeah. The point is that there is an explicit set. Yeah. Of course, there is always some defining equations, but that's the same, right? I mean, I'm trying to define a subvariety. So of course, there are some equations. When I said there are some equations that define the Jacobian locus, I've conveyed no information, right? So the point. No, I mean, there is no unique procedure. We write something which is a natural choice. But in principle, of course, the ideal of relations is much bigger than generated by this. And there is no reason to choose these generators. There is no parameter. I mean, there is combinatorics, but there is no continuous parameter. Okay, that's what. There are combinatorial parameters. Correct. Yeah. I mean, there is some choice of some two torsion point as usual in this business. Maybe more than one two torsion point. Okay? So I could state the Schottky problem on some level cover, then this choice will disappear. But I'm not doing this. Okay? So, yes. Correct. Here I should say the word Gaga principle, right? So the way I defined the map from modular F curves to the modular of abelian varieties is some map which sort of I have to argue is analytic and algebraic, right? The way I define this, I never did this, right? Because I said what a Jacobian of one Riemann surface is. I have to say that if I vary curves, the family of Jacobian, if I have an algebraic family of curves, the family of Jacobians is also algebraic. I have never done this. I will never do this. The deformation theory of curves is something I'm completely ignoring for the purposes of this thing. So I really need to, there is a mystery here on the blackboard. It's the modular of curves. I'm saying, no, it's manifold. I mean, a stack or an orbifold, whatever. I never explained to you why. And that requires work, right? The fact that the moduli of abelian varieties as a stack is rather clear because I've written it as an explicit quotient. So clearly it has a complex structure as a stack, at least, right? Moduli of curves, you could do a nice semester-long course to prove that moduli space of curves is a good Deligne-Mumford stack. This is for abelian varieties, I've clearly presented this as an analytic stack. I need to know it's an algebraic stack. Yeah, I can actually do this explicitly because the theta constants define an explicit embedding of the modular space for abelian varieties with some finite cover thereof into a projective space. But then there is a whole theory behind that. Yeah. I need many things. Yeah. There was another question. Was there another question? No? Okay. Okay. We still have some time. The interlude on the Schottky problem is over. So remember, the goal of this lectures is to present for you Krichy-Vere's solution of a Schottky problem in terms of flexes of Kumho varieties. And the goal of the next hour, which means not just today, but a good chunk of tomorrow, will be to finally state what the theorem is, right, geometrically. And we're not there yet, as you have noticed. So I haven't yet said what the Kumho variety is. I haven't yet said what a flex is. This will all come. Before we go, are there any questions? So again, we have the moduli space of abelian varieties, which is this arithmetically defined object. We have a moduli space of curves. For each curve, we have a Jacobian, which is an abelian variety, but has a beautiful geometric structure. And somehow when I say geometric structure of an abelian variety, I should really think about polarization, because somehow if I think of unpolarized abelian varieties, they're all the same. They're just complex stories. There is no, I mean, it's not true, but somehow I really should think about the polarization. That's the interesting part. And the question is how to figure out if a given abelian variety is a Jacobian of some curve or a Jacobian of a given curve. That's where we're going. So now I'll ignore Schottky problem for a while and I'll switch to more properties of Jacobians of curves for the next hour or so. But there was a question. So the question is whether these explicit equations that I'm getting here are going to get that equation in genus 4. So the answer is they're not going to give you that equation on the nose. This is also not what Schottky wrote. So if you look at Schottky's paper from 1880s, he doesn't write this equation. He writes something which I could write, which I do not remember on the spot, and which involves lots of combinatorial choices of theta characteristics of epsilon deltas, which turns out to be equivalent to this, which is far from obvious, which is the work of Igusa. Igusa was the one who discovered that the Schottky equation is equivalent to that. Our work generalizes not this, but the Schottky equation. So the combinatorics is already there. So if you take what we do in genus 4, you get precisely the Schottky equation in its original combinatorial form, not in that form. There is only a very technical answer to this question. So the question is the nature of the two descriptions different? So this is a nice, somehow a symmetric way. I made no choices here, right? Which is why I wrote this. Schottky was working on a level 2 cover of the moduli of curves related to prim varieties. You need to choose some double cover. This means you choose some two torsion point in the abelian variety, so there is a combinatorial choice. Given that combinatorial choice, Schottky writes down an equation which a posteriori turns out to be independent of the combinatorial choice, but that's not at all clear. We are also making some a posteriori choice of a two torsion point, more than one maybe. It has to be equivalent, but the equation that Schottky writes is not, does not define a divisor without a level structure. So it only defines a divisor on the level structure on a finite cover of the moduli of curves, and you push it down, then you get this. But this requires proof. More questions? Okay. So I want to continue with discussing theta functions on Jacobians. Okay. So remember we have the theta. This is a divisor in pig g minus 1, right? And theta, as was written and erased, is just a set of all things of this form, right? Where pi are points in the curve. That was my description of the theta divisor on the Jacobian. Okay. Now I want to use this. So somehow I didn't write this nicely. So this is just pick g minus 1 of the curve. Okay. So now I want to try to think of theta, which of course sits in the Jacobian, as a function of the curve itself. So let me tell you first that this requires thinking about the curve as sitting inside the Jacobian. So there is a novel Jacobi map that takes a curve C and embeds it in its Jacobian, but sadly it doesn't quite go to peak g minus 1, it goes to peak 1 always. Which of course you can then identify with peak g minus 1, peak naught, but that's not canonical. So what it does is you take a point P and you send it to the point P. Here, this is a point on the curve. Here, this is a divisor on the curve. It's 1 times P. It's a linear combination containing just one point P with coefficient 1. Maybe I should write 1 times P, if that helps, right? It's a divisor. I'm thinking of the point as a divisor on the curve. Okay, so somehow I've embedded the curve in the Jacobian. In peak 1, it's canonically embedded. So wait. You should. This won't suffice. This won't fully suffice. But, yeah. So, if you do this, pretend that this difference between peak 1 and peak g minus 1 was not noticeable, which of course we can't. Then I have theta function, where theta is a divisor on peak g minus 1, but the divisor is the same as a function. So I have a function on the Jacobian, which I can then restrict to the curve. I mean, the degrees of the peaks don't quite match, but never mind. So I have a function on the Jacobian, which I'm going to restrict to a curve via the Abel Jacobi map. So I'll get a function on the curve. So I'd like to know what function on the curve I'm going to get, right? This is the question I'd like to answer. So to make sense of this question, I somehow have to make sure that my degrees are correct. Because I know what the theta function is here, I somehow need to move it to here, right? So I need to take a variable point here in peak 1 and somehow stick it into g minus 1, right? So for that, I need to choose a degree, depending on how I do it, g minus 2, but I actually want to change some sign, so I'll choose a degree g divisor, right? So theta, remember, is a divisor, but it's also the zero locus of a function, right? Theta of tau z is 0, right? So when I write the small theta, I mean the theta function. I'm really thinking of this as a function. So I can think of the following function. Fix P1 through Pg in C and consider theta, and let's say a tau is a Jacobian of C. So the tau is the period matrix of C. Which I have defined last time analytically. And I consider this plus P2 plus dot 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 plus Pg minus Z, say, maybe minus X, as a function of X on the curve.
In other words, you are using a variable C into peak minus 1.
Correct. So what I've really done here is, for convenience, I've put a minus here and shows a minus, right? Because a peak A can always be mapped to peak minus A by changing the sign. That's what I did here. This is for convenience. Okay? And I was going to tell you an exercise about, there will be an exercise precise. I was planning to, Pasha is too fast, but I was planning to give you an exercise in a minute, okay? So this is a function of a point on the curve, right? This now makes sense because this is a divisor of degree g. I subtracted a point, so it became a divisor of degree g minus 1. So this gadget here is a point of peak g minus 1, right? And this is a function. So what is this 0 locus? So observation, this is 0 if x is equal to pi for any I from 1 to g, right? Because if x is equal to some pi, I cancel this point, right? Because say if I look at theta tau, say p1 plus pg minus 1, this is 0, right? Because this is to say that the point p1 plus pg minus 1 lies on the theta divisor, right? And the theta divisor is precisely the locus of sums of g minus 1 points. So if I cancel one of these g points, then I get precisely 0. So this means I know g zeros of this function on the curve, right? Okay. Claim, fact. I'd love to assign this as an exercise, but I don't think it's doable unless you have some further machinery. The divisor of this function is p1 plus pg. This is to say that these are all x. Sorry. So this is to say that these are all the zeros. So all the zeros of the theta function are just these points. So what you need to prove this fact is you need to compute the degree of this function, right? Which you can do if you know something about the intersection number of the theta divisor. So, but we. This is a section of some bundle. So the divisor I define for functions. It's also defined for sections of arbitrary bundles, line bundles. So this function, multi-valued holomorphic function on the curve, has a divisor given by just g points. And there was going to be an easy exercise here. The exercise is that theta is an even function. This is very easy. And the second question is, what is the theta divisor in genus 1? Very explicitly. And then somehow, can you see modularity of theta tau z with respect to tau for genus equal to 1? That has many stars, okay? So this is sort of to allay your fears about changing signs, because I'll be playing this trick again and again. I'll be very sloppy at some point with the signs of arguments of theta functions because it's even, and when I'm not worried about degrees, I won't worry. Okay? Okay, now the last thing I want to say today is that any meromorphic function f from C to P1, non-constant, constant is of course fine, but I don't want to do this, can be expressed in terms of theta functions. Let me try to explain what this is. So I have a function f. Its divisor is going to be equal to some, to the sum of mi pi, where mi I and z, right? I'm writing together the zeros and the poles of this function with multiplicities. So then I can just write down this function f in terms of theta functions, up to a constant factor. No. So claim, more precisely, is f is a product. So let's say this was I from 1 to capital N, I from 1 to N. Oh, I made a bad mistake. I'm sorry. Could we rename this guy is not pi, but xi? I'm sorry. Okay? And I'm just going to write here theta p1 plus dot 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 plus pj minus xi to the power mi for any chosen sufficiently general p1 pg in the curve C. Sufficiently general means they should be all different, they should be generic, they should be different from all the axes. That's a formula. This is just an explicit formula. Proof. If I take one of these terms, the divisor of such a term is just a locus. Sorry. These are different functions. It's not always the same function. Otherwise, it would be a rather boring statement. So I've chosen g minus 1 points completely arbitrarily. Completely arbitrarily here, I really want them to be such that h naught of the corresponding bundle is 1 and not higher. So this is a generic point in the theta divisor, really. And then I've added one of my points xi, and this is my function of x, right? So the divisor of this thing, what is this? Well, this, of course, mi, because it's an mi's power, times wherever this guy vanishes. So this guy vanishes for x equal to this or that. So it's just p1 plus dot 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 plus pg minus 1 plus xi, right? But then this is a divisor of a function. So notice, since the degree of f over 0 and infinity is the same, the sum of mi is just 0, right? That's what I said before, that the divisor of any function has degree 0, right? So now if I take the sum of divisors, which are mi times p1 plus dot 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 plus pg minus 1 plus mi xi, this will cancel because this is just the sum of mi's plus the sum of mi xi, right? So this shows that this product will have the same divisor as this function. But then this means if I take one side, divide by the other, there are not going to be any zeros or poles. But a function on a Riemann surface without any zeros or poles is called a constant. So this means there is a constant here, okay, which I cannot determine, and that's free, right? So that's why I'll stop today, but I want to make some remarks. So this tells you how to recover all functions on Riemann surfaces from theta functions. This is a very weird formula if you pause to think about it, because I've just chosen a random point, p1 plus pg minus 1. It's a random point in the theta divisor, a general one maybe. But there are many choices here. And I wrote this expression, which manifestly seems to depend on these choices. But in reality, as it shows, it's independent of these choices. This will become even more mysterious after the first 20 minutes tomorrow, when something will look clearly wrong on the blackboard. But notice that somehow it all works out correctly, right? I mean, this ambiguity just cancels. And as an exercise not to be discussed, but for your own benefit, try to look at this and try to see how this relates to Abel's theorem. So there is an Abel's theorem for a curve which says that if we take the divisor, so we have the Abel-Jacobi map, maybe I should call it AJ, and of course this extends to a map of divisors. So the statement is that the Abel-Jacobi map of the divisor of F is 0, right? That's one half of Abel's theorem, where the answer is the full statement is if and only if. So this, of course, is related to this and can be deduced from here if you wish and so on. Okay, but I'm not going to discuss that. Okay. I can think about it this way. I can rather normalize things in a different way. So I will ignore this constant. Yes. The constant does depend on P1, Pg minus. The constant will depend on P1, Pg minus 1. Yes. Yes. But that's not how I will want to think about such things. That's it for today. Thank you.
All right, let's take them. There were some questions during the lecture, but are there any other questions? Let me check if there are any questions online. Okay. Everything seems to be very, very clear. So thank you very much again, and we have a good go.
Thank you.
Okay, so let us continue. And we have now the second lecture by Professor Rettinghoff.
Okay, so let me remind what we did last time. So last time we proved the Grothendieck's theorem. That vector bundles on projective line are of the form O of M1 plus so on plus O of Mn. So of rank n. Where M1, Mn are integers. And so any vector bundle on P1 can be uniquely written in this form for unique numbers M1 through Mn. And I want to start with explaining how this generalizes to an arbitrary connected reductive group. And to do so, I want to reformulate this result in a way that will be easy to extend to any connected reductive group. So recall, so this is the same as GLN bundles. And GLN is the group of invertible n by n matrices. So it contains a maximal torus T, which is diagonal matrices with non-zero entries on the diagonal. And so T is a, let's work over complex numbers. So then this is going to be C star to the n. And what this theorem says is that every, so if I call GLN G, that every G bundle on P1 is associated to a T bundle. Which means that the structure group of this bundle, as people say, reduces to the torus. But moreover, so because so what are T bundles? Well, T is a product of C stars, so a T bundle is just a product of C star bundles, and a C star bundle is a line bundle, so it's of the form O of M. But actually, more than that, the same G bundle can come from a bunch of different T bundles. Because when you talk about a T bundle, it actually matters in what order you write these numbers. But for a G bundle, it doesn't. And so, so this means that moreover, if E1 and E2 are T bundles on P1, and well, then they're associated bundles E1 over T with G is isomorphic to E2 over T with G if and only if there exists a permutation sigma in the symmetric group such that E1 is isomorphic to sigma of E2. And so in fact, in this form, this theorem generalizes straightforwardly to arbitrary reductive group. So now, if G is a connected reductive group, so I'm working over algebraically closed field right now, and T is a maximal torus, so then we have the normalizer of this maximal torus inside G, and the Weil group is the quotient of the normalizer by the torus itself. Because this group is abelian, it acts on T. And the theorem says that any G bundle on P1 is associated to a T bundle and the same thing is true. And E1 T G is isomorphic to E2 T G if and only if E1 equals to W of E2 for some element of the Weil group. For GLN, the Weil group is the symmetric group, and so it reduces to this state. I'm not going to prove it, but that's what can be done, and proof can be basically reduced to the case of vector bundles by considering representations. So I'm not going to go into that. And so what this says is, so now suppose T is a torus. G. Yes. Okay, so so suppose T is a torus. So as I said, torus is isomorphic to C star to the n. But it is so in many different ways because there is an SLN Z acting. And so let me just say a torus without choosing this identification. Then how to classify T bundles on P1. Well, we know T is isomorphic to C star to the n, so this is just an n tuple of integers. So this is in bijection with Z to the n, but non-canonically. What is it canonically? Well, I claim canonically it is something that is called the co-character lattice X lower star of T, which is by definition hom from C star to T. So it's a group homomorphisms. Of course, this is C star to the n, and so this is just z to the n, but canonically it is this. And it's quite clear why, just by our definition. Remember that such a bundle is defined by a transition map from chart u infinity, which means 0, to chart u0, which means infinity, g of z. So in G is a map from C star into our group. But of course, any map like that, well, it's isomorphic to C star to the n. And any map like that has the form z goes to, well, we discussed for each coordinate, we're going to have a constant times z to the n. So we're going to have C1 z to the m1, C2 z to the m2, Cn z to the mn. And these constants are non-zero, and they can be rescaled to be 1. And so in this case, we just get, without these constants, and this is a group homomorphism. So it is a co-character. So this is called the co-character lattice. Of T. And canonically, our bundles are classified by this co-character lattice. So theorem says that G bundles on P1 are classified by the co-characters of T modulo the Walk group. But of course, this can be so a remark is the co-characters of the maximal torus is the same thing as the characters of the dual torus, which is the same as weights for the dual Langlands dual group. So these are weight lattice let me call it lambda check of the Langlands dual group G check. So a connected reductive group by definition is defined by what is called a root datum. And a root datum is a root system, dual root system, and the weight lattice and the dual weight lattice. So there is a root datum is a thing that has an involution where we can exchange roots and co-roots, weights and co-weights. And that exchanges the group G with the Langlands dual group. So for example, it exchanges SLN with PGLN, and it exchanges symplectic and orthogonal groups, so SP2N and SO to N plus 1. Langlands duality is a deep connection between objects related to G and some objects related to G check. And actually, this is a baby example of a Langlands duality. When bundles, G bundles on P1 are classified by weights for the, so basically by represent, so this X star of T mod W is the same as lambda mod W. So this group G and G check always have the same Wal group. And this is the same as lambda check plus, which is dominant integral weights. Which label irreducible representations. Irreducible finite dimensional representations. So we see that there is a bijection between principal G bundles on P1 and so we have a bijection between principal G bundles on P1 and irreducible representations of the dual group G check And this is a very baby example of Langland's duality. Of course, it extends much further and much deeper than that. Okay, so this is just one comment. So now we talked last time also about the following object. So X was a smooth, irreducible projective curve. Over some field K, and G is a split connected reductive group over K. So in this case, we don't have to assume that K is algebraically closed, but split groups is the same. They're labeled by the same data, namely root system in the weight lattice and core root system dual weight lattice. So we have this pair, and to this thing we attached something that I didn't really define in full detail, but at least defined as a functor of points. And this is the stack of bundles, bun G of X. So moduli stack of G bundles on X. So this is a very complicated object, and I explained some of the complications that it comes with, but luckily, many of these complications will not be very important for us. However, I would like to describe this stack as a set a little bit more explicitly. And so this topic is called the double quotient realization of this bun G of X. So just want to make it a little bit more explicit. So for simplicity, let us assume first that G is semi-simple. In this case, we saw that so any bundle by the theorem of Harder that I quoted trivializes once you take out a point. So let's fix a point. So let me first consider the case algebraically closed field. So then we always have a point. And when I write an x, it's really x of k, but I'm going to skip it. And then we have, we can cover x by two charts. So let's draw x. So it's a curve. So if our field is complex, it's a Riemann surface. And then this is our point x. And I'm going to cover it by two charts. So one chart is a disk around this point, and the other chart is the complement of this point. Well, that's if we are working in complex analytic setting, then we can just take a small disk. But in algebraic geometry, we do not have small disks, but we have formal disks. And we can do the same thing by using formal disks. And that we can do over arbitrary field. So the two charts are, first of all, x minus x. This is just the affine curve obtained when you delete this point. And formal disk d sub x around x. But if you are not comfortable with formal disks and you like more complicated things like analytic disks, you can think about them. Okay, so so they do cover our curve, which you can say algebraically as
So it makes sense over any field. And so we can compute bundles by using this cover. If we have only two open sets, we do not have to use a cocycle condition. We just need to fix one transition map. So for this purpose, we need to say what the intersection of these two things are. And you might guess what it is. So if you think about analytic disk, the intersection is, of course, everything except the center of the disk. So this is called the punctured disk. So this is the punctured disk. But again, if this disk is formal, well, it has only one closed point, which is this point, and you deleted it, so it sounds like you get an empty set. Well, you don't get an empty set because you should talk about it in the language of algebraic geometry, which is the language of rings of functions. And so, so functions on the first set, O of x minus x, this is clear. This is just regular functions on this affine curve. X minus x. And I'm going to denote this by R. And then O of dx is functions on the formal disk, which is the following, that if you choose a coordinate on this disk, so if t is a formal coordinate, at x, for example, you can choose an ordinary coordinate and view it as a formal coordinate, then O of dx is identified using this t with functions on the standard disk. And standard disk functions there are just formal power series in t. And then you can take O of dx times dx star, which is a punctured disk. And this is, so if we delete things from ordinary disk, we get Laurent series. But, well, there are conditions on convergence of them in the analytic world, and they could be infinite in both directions. For formal disks, in order, we should take formal Laurent series, but formal Laurent series do not form a ring in general if you consider them infinite in both directions. So you should take series which are finite in the negative direction. And that is a ring and moreover a field. So it's a field of functions of formal Laurent series. And well, the fact that this is intersection means that we should have inclusion of both of these rings inside K of t, inside this field. So this will be called capital K, and this will be called O. And so, of course, O is included in K. So this is, if you like, the ring of integers. So we have a non-Archimedean valuation, which is the order of this series at 0, and O is the set of series with non-negative valuation. And also, we can embed these functions on x minus x into K. And this is obtained by taking the Laurent expansion. So, of course, to take Laurent expansion and end up here, you need to choose a coordinate. But it's easy to show that if you think about them canonically as this, without choosing coordinate, then this inclusion doesn't depend on the choice of the coordinate. It's not on? It wasn't on. Ah, okay. So bundles E are defined by transition map G from one of these charts to the other. So let's say from the disk to x minus x. And so this is I can write it in terms of this coordinate. So this G of, it will lie in the group G points over this field K. So it maps from this punctured disk to G is just this group of now it works. What? Works? Okay. Good. Why is it called loop group? Okay, well, you should think again about this punctured disk. So punctured disk is like an annulus. It's a disk, but from which you took out the middle. So, and we are looking at, for complex numbers, if you're working analytically, about holomorphic mappings of this disk into the group G. But now, of course, a holomorphic mapping like that is determined by its restriction to some circle, real circle, going around this point. Because Fourier expansion on the circle is the same as the Laurent expansion over this disk. And so this is really mappings of the circle into G in the analytic case with some analyticity properties. And that's why it's called the loop group. Other questions? Okay. So this is orbits. And we can generalize this. So we can, instead of removing one point, why should we remove just one point? We can remove any finite set of points. So suppose S in X is a finite subset. And then we can consider two charts. So first of all, affine curve X minus S. So I want the subset to be non-empty. So this is going to be an affine curve. And the second is a disjoint union over points in my set S of the disks D sub X. And I'm going to, for each of these points, I'm going to choose coordinates. Well, maybe I don't need to go into these details. Anyway, there are these two charts. So this is like U1, and this is U2. And then the intersection of these charts, U1 intersects with U2, will be the disjoint union of the punctured disks. And then, so you will get the following presentation. Bond G of X is going to be the quotient. So we need to take the group G of G-valued functions on this product, on this union, which is just the product over X in S of G of the disks dx star. On this side, we will take the product over X in S of G of dx. And on this side, we will have G of R. I can write it algebraically like that, or I can also write it geometrically. So I can write G of dx star, G of dx, and G of x minus x. And so here I can also write it this way, but there is a product here, and here is G of x minus x. So that's also a valid presentation for any finite subset S. But now this is for semi-simple groups, which have the property that we can trivialize any bundle by removing just one point. Remember that for G equals to C star, which is kind of the simplest example of reductive group, that's not the case. There is no set S that we can remove to trivialize all possible bundles. And so in that case, we need to consider, we need to remove all points. Well, you might think that if you take a curve and remove from it all points, you get an empty set, but not in algebraic geometry. So in algebraic geometry, when you remove a finite set of points, this means that you allow your functions to have poles at those points. So if you remove all points, this means that you allow your functions to have poles anywhere, which means that you consider arbitrary meromorphic or rational functions. So this means that the ring R should be replaced, which is functions on x minus x, or x minus s, should be replaced just by the field of rational functions on your curve. So further generalization is you can take a colimit with respect to this set S. So take a union over all finite subsets S. And so that what you will get is the following presentation. So bond G of X will be the double quotient. So here is going to be a product over all points of your curve of G of dx. Here will be G of the field of functions. And here there is going to be a product over x and x of G of dx star. But here there will be a little technical detail, which is a prime over this product. So what does it mean, prime? It means that almost all factors. So what is a product? Product is a collection of elements of all these things. And product prime is a restricted product, which means that only finitely many of them actually have a pole, actually have negative coefficients. So product prime means that only finitely many coordinates are not in G of dx. So have a pole. So this condition comes from the fact that we're removing all points, but we're taking a limit from finite subsets. Okay, and so this this is our algebraically closed field. And if your field is not algebraically closed, so if K is not algebraically closed, question? This is field, yes. I don't quite understand the question. Yeah, well, this is of K. Of little k. So if K is not algebraically closed, then we should do the same thing, but we should but in this case we should take sets S inside of X of K bar, algebraic closure, which are Galois invariant. And so so then we will get bond G of X of K is going to be the product is going to be X of K bar modulo the Galois group and here it's going to be product, and here it's going to be G of K of X. And so if K is a finite field, for example, then this K of X, it was just called a global field, which means that all completions of this field with respect to valuations are local fields, locally compact topological fields. And and this thing is actually a product overall valuations of this field K of X. So this field can be denoted by F. It's a global field. So what we get is the following double quotient. So here is going to be G of the product prime of evaluations of F of fields, local fields, FV. So if you have a valuation, so what are valuations on this field, K of X? They are, we can evaluate this field by taking order of a function at a point of X over some extension of K. These are all valuations. And so we take G over the product here, modulo G over the product over V in valuations of F of OV. And so this is an integer in FV. And then here we take G of F. So that's the presentation that we've got. And this is what goes under the name of arithmetic quotient. And the reason is that a similar quotient arises in number theory. So this is a global field of characteristic P, because K is a finite field. But there are also global field of characteristic 0. And those are just number fields, which are finite extensions of Q. And you can run the same story for them. So let me just comment on it, because it's not going to be very important, but at least for motivation, it will be. Thanks. So for motivation, it will be at least somewhat important. So definition, if F is a global field, then the ring of Adels AF is this product prime of F sub V, where V in valuations of F. So over fields of characteristic P, global fields of characteristic P, they all have this form. It is literally that. Over number fields, there are two kinds of valuations, which are Archimedean valuations, and which arise from embeddings of your field into real and complex numbers, and taking the usual absolute value, and also non-Archimedean valuations, which correspond to basically p-adic valuations. And prime means in this case that, so being an integer makes sense in non-Archimedean valuations. And so there should be finitely many instances like that. And then O F. So let us call it A. And OA is the product over V in valuation non-Archimedean of F or V. So rings of integers in non-Archimedean fields FV. And so in this case, all valuations are non-Archimedean, so you don't have to worry about it. And then you can define this arithmetic quotient M, which is your group G over A, modulo G over OA, and defined in modulo G of F. And so this is a generalization. So if F equals to K of X, we get Bon G of X of K. So M is equal to this. Okay, and so example, which is not of this type, is, well, we should take a field of characteristic 0, so F equals Q. So in this case, the Archimedean valuations so all the primes, which correspond to embeddings of Q into p-adic field QP, and also infinity, which corresponds to the usual absolute value valuation, which corresponds to embeddings of Q. If you complete Q with respect to that valuation, you get real numbers. And so you get, so this A, in this case, is just R times the product over prime with a prime QP, which means that only finitely many of them fail to be in ZP. And OA is, well, here we don't have ring of integers because it's Archimedean. The other are not Archimedean. So that's the product over the primes P, ZP. And so we will get our quotient is going to be G of R times the product prime of G of QP, quotient G of ZP, and product prime in this case means that almost all elements are 1, because if this coordinate is in here, then we will get 1. And then this is going to be modulo G of Z. And, well, it is known that so G of Z is dense in this product, and therefore actually the product. So this whole group maps to the identity. So this is just a quotient of, I'm sorry, G of Q. And so so what this is well, there is some. This is non-trivial, but it's proved in number theory that this is the same. So the map from G of R into here is surjective, and so this is just G of R. So there is a G of R action on the right, and this is just G of R modulo G of Z. So so this is a manifold which, for example, if G is SP2N, this arose in the so we'll get SP2NR modulo SP2NZ. And if you also take quotient by unitary group, then as Sam explained in the previous lecture, this is the moduli of abelian variety of genus N. So this is the arithmetic quotients in number theory. And basically, well, Langland's program arose as an attempt to, prove some results in number theory, for which you need to. So another example, of course, classical example is G equals to SL2. And in this case, you get SL2. So this is a special case of genus 1. And so if you quotient by U1, well, this is the upper half plane. And so this is moduli of elliptic curves, or M1. So for me, this distinction is not going to matter. And this is where modular forms live. So modular forms have important applications in number theory, and Langlands wanted to understand the modular forms and their higher rank generalizations, and for this purpose, one needs to work on this thing, and actually, but then you might as well work on this quotient for any global field, and in particular for global fields of positive characteristic, which are these, and in this case, it reduces to algebraic geometry, which is moduli of bundles. And this is very good because we know a lot more about algebraic geometry than we do about number theory. And actually, it also turns out that sometimes, I mean, for example, there was an important conjecture in this theory which Langlands couldn't prove, and it was unproved for 45 or 50 years, which was called fundamental lemma about this arithmetic situation. But it was proved by using this analogous situation in characteristic P using algebraic geometry. So this is just a little aside. Of course, we are not going to talk about any of this because it's very complicated, and I'm not qualified to give a course about this. So, but what I want to say is that this presentation is already good for any reductive group, not necessarily semi-simple, because now we removed all the points. And of course, if we remove all the points and go to the field of functions, then any vector bundle or any G bundle will be trivialized. Because any bundle, as I explained, is Zariski locally trivial. So in particular, the Jacobian of X can be written as this complicated quotient for the case of G equals to GL1. And I invite you to think about, so if G equal to GL1, what you obtain is that Jacobian of X is, well, in which I pick a 0, so it's a group structure, is a multiplicative group of A, which means invertible elements here, modulo multiplicative group of the ring of integers, and modulo well, let's work over C, then it will be like that. And so this, you should think about this and discover that this is in fact the group of divisors on X. And this is the subgroup of principal divisors. Well, at least modulo scaling. So and so this is the presentation that Sam explained in his lecture. All right. So now I want to talk about, start talking about Hitchin system, which is the main thing I want to discuss. And for this purpose, well, Hitchin system is an integrable system. Integrable systems live on symplectic manifolds. But we don't have a symplectic manifold yet. So we need to introduce one. And of course, the most common symplectic manifolds are cotangent bundles of ordinary manifolds. So we want to define cotangent bundle of band G of X. But actually, of course, like I explained, band G of X is not a manifold, not even a scheme. It is a certain very singular object. Well, it is a smooth stack, which is a quotient of a smooth, locally it's quotient of a smooth variety by a group, by an algebraic group. And for such things, you can define cotangent bundle, which is another stack. And there are cotangent spaces which you can define, which are actually complexes. But this is not what I want to do. I actually want to do down-to-earth theory of integrable systems and study usual symplectic manifolds. Well, luckily, what happens is that there is an open set. So I'm going to assume that the genus bigger or equal to 2. And I'm going to take, let's say G is going to be simple. And let's say adjoint, just to make things very simple. So which means there is no center. So in this case, well, I said that this was a stack. And the main feature of a stack compared to scheme is that points have automorphisms. Well, it turns out that in this situation, if you pick a generic bundle, it doesn't have automorphism. So automorphism group is trivial. And so generic and I will explain something about what this means, but generic bundles have trivial automorphism group. So this means that they correspond to a locus where in this presentation as a quotient of a variety by a group, the group is going to act freely. So stabilizers are trivial. And they form an algebraic variety, smooth algebraic variety. Bon G of X with a circle. So as long as we restrict to some open set, this stack, which is a functor of points, actually is representable by some variety. And I should explain what this generic means. So there are many, there are many ways to choose this open set. One nice way is to consider so-called stable bundles. So let's consider an example where G equals to, let's say, PGLN. So this means that G bundles are just rank n vector bundles. Modulo tensoring with line bundles. And for defining stable, it's not going to matter modular line bundles because stability doesn't change when you tensor your bundle with a line bundle. So, so there is a notion of a slope of a vector bundle. So if E is a vector bundle on X, then we have two integers that we can attach to it. One is the degree, which is the first Chorn class. And the other, so this is called D of E. And the other is the rank, dimension of the fiber, which is denoted by R of E. And then we can define the slope, which is a rational number, so which is mu of E. And this is degree of E divided by the rank of E. And the definition says that E is stable if for every subbundle E prime inside E, which is strictly contained in E and not zero, because for zero bundle we cannot define this ratio, but for every such subbundle, the slope of E prime is strictly less than the slope of E. But that's a very important definition. And there is a similar definition for other groups, but I will not give it. It's technical. And the precise meaning of this generic, one of the good ways to define this generic is to consider stable bundles. So the theorem is that stable bundles form a smooth variety which is an open subset of band G. PGLN bundles, yes. And they have trivial automorphisms. They have trivial automorphism. What? So what, I'm sorry? Yeah, no, but it's no, it is not. It's only defined modulo n, because when you tensor it with a line bundle, the degree changes by n times the degree of this line bundle. But if we choose a vector bundle, so it's an exercise. If L is a line bundle and E is a vector bundle, then E is stable if and only if E tensor L is stable. And this means that while this degree is not defined, the notion of stability is defined. Okay, so so it's a subset of bond G of X, where G equals to PGLN. And so generic, so this means the generic bundle is stable. And has no non-trivial automorphisms. And so this set bond G circ of X will denote the moduli of stable bundles. So which is a smooth variety. And so one can consider, therefore, MG circle, which is the cotangent bundle of bond G circle of X. And so Hitchin system will initially live on this cotangent bundle, but actually it turns out that there is a partial compactification of this, which is also a symplectic variety, and the Hitchin system naturally lives on this compactification. This is actually a very common phenomenon in integrable system, that, you know, if you with pedestrian approach to integrable system, when you write formulas, normally you define it on a certain rather simple variety, you know, affine space, or maybe some open subset of affine space when some coordinates are not equal to each other. But then many integrable systems naturally extend to certain compactifications of the original variety on which you define them. And this is a kind of deep geometric fact. So they know about geometry. That's a very important feature of integrable systems. And this is not an exception. This happens here as well. So there is a compactification of this space, partial compactification, which is called the Hitchin moduli space. And the system will extend to that space. But before we do anything, we really should ask ourselves, okay, we have a variety, but variety has a dimension. So what is the dimension? And for this purpose, we need to compute the tangent or cotangent space, because, of course, dimension of the variety is equal to the dimension of the tangent or cotangent space to this variety at a point. So what is the tangent space at a bundle E of this bond G circle of X? Well, this is a very standard thing. So tangent vector means that we are going to move. So this is our moduli space of bundles. And there is some bundle E. And then we look at tangent vectors. So what does it mean? Tangent vectors means that we kind of can move in that direction and deform our bundle. So this is deformations. This is just the deformation space of this bundle E. And it's easy to see that this deformation space. So deformation. So it's an exercise that deformations of the bundle E are classified by H1 of X with coefficients in adjoint bundle. So what is adjoint bundle? So I told you that for every representation of your group G, if you have a G bundle, you can define the vector bundle associated to this representation and to your bundle. And in particular, you can take the adjoint representation. And that will be the adjoint bundle. So here is an example what happened for GLN. For any G, actually, it doesn't matter, and it doesn't matter that it is stable. So, but if it's not stable, then this will kind of classify first-order deformations, and then it may not extend. So, but the calculation is the same, and so so here is an example. So let's take G equals to GLN. This is not semi-simple, but never mind. Well, maybe PGLN, okay. So, so in this case, well, okay, so let's take GLN. So in this case, it's vector bundles. And so in this case, deformations of E is like deformations over of projective modules over the sheaf of functions on X of rank n. And deformations over modules over any ring are classified by X1 from the module to itself. Because what does it mean, deformation? Deformation means that you define some module over the ring of dual numbers, k of h over h squared, which modulo h gives you a module. But this module, if you consider this, and it is free as a k of h over h squared module. So if you view it as a module over k, it's an extension of E by itself. So this is how deformations work. And so deformations of E is just going to be x1 of EE, which is the same thing as x1. So we can move E to the other side, will be E star. So from the trivial bundle, from O to E star tensor E. And this is exactly the adjoint of E, because E is a GLN bundle. And this is the same as H1 of X with coefficients in adjoint of E. But this calculation is easy to generalize to any group. Huh? I cannot hear. Can you speak up? Okay, so if you have rho is a representation of G to GLN, and E is a G bundle, then we can define E sub rho. This is corresponding GLN bundle, which is associated. So the transition function G goes to rho of G. And in particular, we can take rho is the adjoint representation. So action of the group G on its Lie algebra. Okay. All right, and so this classifies deformation. And so we get that the tangent space is equal to this H1. And this means that the cotangent space at E of 1 G of X circle is the dual of this space. So it's H1 of X with coefficients in adjoint representation adjoint bundle of E dual. But then we have Serre duality, which says that this is the same as H0 of X with coefficients in the dual bundle tensored with the canonical bundle, which is a bundle of 1 forms on X. But this is the same. Of course, there is a trace form on the Lie algebra, the Killing form, and therefore the adjoint bundle has also an invariant inner product, so it is self-dual. And so what we get is that this is equal to H0 of X. So I think it is customary to write Kx as a first factor, tensor product with the adjoint E. And so what is this? This has a very vivid geometric interpretation. So these are 1 forms on X, holomorphic 1 forms on X with coefficients in the adjoint bundle. So as objects on X, they are 1 forms, but they valued also in the adjoint bundle. And such objects have a name, because they appeared in physics in the work of Higgs, and so they are called Higgs fields. So this is the space of Higgs fields for this bundle. And so now I'm ready to define the Hitchin integrable system. So for this purpose, I first need to recall something about Lie algebras. Because adjoint of E is valued in the adjoint representation, which is the Lie algebra G. So recollection about Lie algebras. So, yes. Oh, I'm sorry. Yeah. I was going to say what dimension is. Okay, thank you. So what is the dimension of this H1 of X with coefficients in Kx, tensor product with endomorphisms of E? H0, I'm sorry. Well, for generic bundle, so first of all, we have the Euler characteristic of which is the dimension of H0 minus dimension of H1. And as always in geometry, Euler characteristic is a very robust thing. It does not change under deformations. So this is deformation invariant. And but for generic bundles, so this is 0 for generic bundles. So it requires some, arguments, but one can show this. And this is logical because, well, this thing is invariant. So if you take generic bundles, if you take a non-generic one, this thing will be positive, and this thing will be bigger. So that's what happens when you have singularities. Your tangent space at a singularity actually is bigger than the tangent space for generic point. So really, it's equal to the dimension of H0. And so you need to compute the Euler characteristic. But Euler characteristic can be computed. So let's say we have, so the Euler characteristic Well, if your group is adjoint, then you have to be a little bit more careful because you have several connected components of bond G. But if the group is simply connected, then well, you can compute chi for trivial bundle because it's deformation invariant, and for trivial bundle, so then it is dimension of H0 of X with coefficients in Kx times the dimension of G, because this is just a copy of G in that, sorry, adjoint E. So this is just a copy of G, and so this is the space of one forms. Well, for the trivial bundle, so you need to compute dimension of H0 minus dimension of H1. But this is G, because this is the space of one forms, holomorphic differentials on your Riemann surface. And this is, by Serre duality, it is H0 of X, Kx inverse times Kx, so just O dual, and this is just one dimensional. So you get 1. And so G times dim G minus dim G, so this is G minus 1 times the dimension of G. And so this is the answer for the dimension of this for semi-simple groups. Huh? Trivial bundle is not generic, but the Euler characteristic is the same as for generic. Okay, so now if you have a reductive group, yes. Yes, so what I'm saying is, first of all, we have a notion of Euler characteristic. Euler characteristic is a topological invariant, so it does not change when we deform the bundle. In particular, it's going to be the same for all bundles, even for non-generic ones. On the other hand, for generic bundles, this H1 is going to be 0, and H0 is going to be the smallest possible. So for generic bundles, Euler characteristic coincides with dimension of H0. And so, so then we compute the Euler characteristic in the simple case for the trivial bundle and get this number. And I should say that, so if G equals to C star, then bond G of X is just, so if you forget about the automorphism groups, it is just the Jacobian of X, which has dimension G. And so this means that, so here is G times the dimension of the group. And so this means that if your group is mixed, it's a mixture of a semi-simple and abelian, so any reductive group. So G general reductive group. So we get dimension of bond equals to G minus 1 times the dimension of the Lie algebra plus dimension of the center of this Lie algebra. So because for each commutative component, we get an extra unit. We have G instead of G minus 1. And so in particular, in example, if G equals to general linear group, which is, yes? Yes. No. This is already, G minus 1 is already taken into account here. Okay, so if G equals to GLN, what we will get is G minus 1 times n squared plus 1. So that will be the dimension. Okay, so now I use that. There is no. If G is not semi-simple, then generic bundles have automorphisms, and so this will never be 0 actually. So like, let's consider that case. So if G is C star, then this is just a one-dimensional space, and so you're just computing the Euler characteristic of the canonical bundle, which is, so if you compute Euler characteristic, this is going to be G and this is going to be 1. So if you compute the difference, it is G minus 1. But if you think about Jacobian just as a variety without considering the automorphisms, it is G dimensional. Yes? Yeah, you can write it like this. G minus 1, this is what Kohler was suggesting, dimension of G semi-simple plus G times dimension of the center. Huh? But this is also correct. All right, so, and so now let me just give I finish by giving definition of the Hitchin integrable system, and then we will discuss integrability, prove it, compute examples next time. So Hitchin integrable system on T star of Ban G of X circle. So what is an integrable system? This is just a collection of Poisson commuting functions whose number is equal to the dimension, half the dimension of your symplectic manifold. So in this case, the dimension of this base. And which are functionally independent. And so what, in other words, you can think of it as if you make these functions into a vector, this means it's a map to it's a map to a vector space of dimension equal to the dimension of this thing, which is a Lagrangian fibration. Which, being Lagrangian fibration, at least generically, is equivalent to these functions being functionally independent and in involution. So they Poisson commute. So for this purpose, so let me do it in the case of GLN, or maybe SLN. So in this case, the dimension of Ban is equal to n squared minus 1 times G minus 1. And in this case, so what is this thing? This is a set of pairs, E phi, where E is a stable bundle, and phi is a Higgs field. So phi is a one form on X with coefficients in endomorphism. So phi 0, which means it is trace 0 part. So this is for SLN or for PGLN, it doesn't really matter in this case. And so we define, so Hitchin map is P from cotangent bundle of one G of X circle. And this maps into the following space. It is a direct sum from I equals 2, from I equals 1 to n minus 1, H0 of Kx, of X, with coefficients in Kx to the power I plus 1. Now, by the Riemann-Roch theorem, this has dimension equal to 2I plus 1 times G minus 1. And so this whole thing has dimension, the sum of these things. So this has dimension, sum of 2I plus 1 is n squared minus 1. So we get n squared minus 1, G minus 1. That's exactly what we need. It's the same as the dimension of this thing. And this space is called the Hitchin base. So usually denoted Hitch. So it's a vector space. And the map is given by the following. P of E phi is equal to the trace of phi squared, trace of phi cubed, up to trace of phi to the n. Trace of phi to the n. So, so note that since phi is a one form, then trace of phi squared is a quadratic differential. Trace of phi cubed is a cubic differential, and so on. So that's exactly a map of this form. And the theorem of Hitchin is that this is an integrable system. So coordinates are Poisson commutative and functionally independent. It's a very large class of systems because it's attached to any curve. Yes? Well, the role is that we take it, well, of course it also makes sense for complex geometry. So it can be complex differential geometry. But the role is that we're taking H0. So these are global objects. They're global quadratic differentials. And we're using Riemann-Roch theorem to show that the dimension is this. Yeah, absolutely. And Hitchin wrote his paper in the setting of complex differential geometry. But again, as I explained, that because of the Gaga theorem, there is it is equivalent to work on complex differential geometry or in algebraic geometry over any field of characteristic 0. And in fact, but this makes sense in algebraic geometry, so you can even do it over fields of characteristic P. Can be done over other fields, yes. And so, I will stop here, and then next time we are going to prove this theorem. We will generalize it to other groups, and then we will consider generalization to bundles. So this is a bit complicated because we have to consider curves of genus greater than 1, though they're rather complicated, not so convenient to compute with, but we will consider bundles with parabolic structures, which is a kind of more general case, so-called ramified case. And this will allow us to consider bundles on P1. So P1 doesn't satisfy our assumption. It doesn't have stable bundles. But if you add parabolic structures, it will have stable bundles. And we will be able to work on spaces which are much more easy to work with by hand. And in particular, we will consider the case of GL2 with parabolic structure. And we will show that in this case, we obtain a famous integrable, well-known integrable system, which is called the Garnier system. And so we will actually calculate the Hamiltonians in coordinates. Thank you.
Let's thank Pavel. Are there any additional questions? So the question is, what's the definition of coordinates on the cotangent bundle?
So we don't need coordinates. There is a canonical symplectic structure on cotangent bundle for the manifold on variety also. And so this is, to formulate this theorem, we do not need coordinates. That's actually a very, Hitchin base is a vector space. So if you choose a basis, you will have coordinates. And those are algebraically independent. These are integrals. These are going to be first integrals of the Hitchin system. Hitchin system does not have a distinguished Hamiltonian. You can take any of the coordinates and use it. So there is, you really should think about all flows for all of the integrals. Yes?
So the question was, what's the definition of generic bundle?
Yeah. So generic for me will be stable bundle. For semi-simple groups, it will be, well, actually, even for reductive groups, the definition will be stable bundles. They don't always exist. Like for P1, for example, there is no stable bundles. But for P1 with parabolic structures, we will introduce the notion of stability, and there will be stable bundles. They will satisfy the same property, and we will obtain interesting integrable systems in the same way. So the point is that if you don't have stable bundles because you have too many automorphisms, so in this situation, you want to rigidify your problem, which means to fix, for example, you can fix elements in fibers at several points. And this will make a lot of bundles which were not stable into stable bundles. And then you can do this, play this game, and you will get lots and lots of interesting integrable systems. You will even get more interesting ones if you also fix derivatives, not just points, but also derivatives and second derivatives at those points. So that's called wild ramification. And this will give you really interesting things. For example, you can get affine Toda systems this way for any group, and many others.
Okay.
No, you will, okay, same change of stability condition. So there are various definitions of stability, which may differ. For example, for parabolic structures, you can fix so-called weights, and there will be different stability conditions. But generic bundles are going to be stable with respect to any condition, basically. And this, what you will get doesn't depend too much on these conditions. I mean, what depends on these conditions is what kind of open set you will take. So you know, you take some opens, like which points you are going to include. And that's not so important as long as we know what happens on the generic locus.
Other questions? No. I'm sorry, we cannot hear you from there.
When take trace, what? Trace of phi is 0, right? But trace of phi squared is not 0. I cannot hear. I'm sorry.
Yeah. Okay. So I'm sorry. We would have a mic at the end of the room next time, but it's just impossible to hear. Question?
It's this takes more than 2 minutes to explain. So.
Okay. Maybe one more question and lunch. Comment.
So he was asking the square of the one. So he was asking the square of a one form should be 0 on the curve.
The square of a one form. No, it's not. It's not exterior square. It's a tensor. So Kx is a line bundle, and so when we take like sections is something times dx, then sections of square is not dx wedge dx, which is indeed 0, but dx tensor dx. So we have a tensor powers instead of wedge powers. Ah, yes. Okay.
All right. I suggest the remaining questions can be moved into discussion sections. And let's thank Pavel again and have a lunch break.
Okay. Very slow. Oy.